Hi, students. So I wanted to create this video for you guys because there are these concepts that are spread out over 3, 4 videos in Khan Academy, and I think it would be better, my opinion, that some of those concepts be put together into a single video, just because I feel like so many of those concepts are so interconnected, so related, and some of the skills required are so similar that it would make sense to put it all together. Additionally, there's actually no exercises within Khan Academy related to this topic, so that's another reason for why I want to do this, to create this, as well as make a separate assignment, which is the Google form that I want you to fill out after having taken notes on this and after having watched this. Okay. All right. So in this video, what I'm going to try to cover are these two topics, or this concept here, which is this idea of applying concepts related to chords perpendicular to radii, and lines tangent to circles. So I'm going to try to cover that in the next couple minutes. If you want to watch Sal Khan, who's the narrator of Khan Academy, go through this in detail as far as the proof of what I'm about to show you, I highly encourage you to do that. Please go and watch it, okay? Because I think it is very enriching. But anyway, here it is. So I want you to observe with me for a moment, okay? I have this situation where if AC is a chord where AE is equal to EC, then the radius is going to be blank to the chord, okay? Now, keep in mind, okay, what exactly is a chord? A chord is a line drawn from one part of a circle to another, so AC here is the chord. And what I'm telling you right now is that chord, okay, those two segments, AE and EC, are going to be congruent. So as a result of this, okay, what can we conclude about the relationship between the radius and the chord? Now, I need you to look at this. Just look at it with your eyes, okay? What do you think is going to happen between the angle formed by the radius and the chord? Use your eyes and judge for yourself, okay? And this is a really easy way for you to remember this fact, okay? If you're thinking that the radius and the chord are going to be perpendicular to one another, you're absolutely right. So let's write down perpendicular. So if a radius bisects a chord, then the chord and the radius are going to be perpendicular to one another, okay? Which is what this theorem here is saying. If AC is a chord where AE is equal to EC, then the radius is perpendicular to that chord. They are going to be perpendicular to one another. All right, so there's a second half to this, okay? So the flip side of this, okay, is we're going to start off with if a radius is perpendicular. Now I'm telling you that they're perpendicular to the chord, okay? So now the given is I'm telling you that the radius and chord are going to be perpendicular. Then what will happen between the radius and the chord? So this is actually going in reverse with that statement from above. Let's just think about this for a moment, okay? If we have the chord and the radius are going to be perpendicular, then the result is the radius will, pause for a moment, okay? If you pause the video if you want to think about this. Welcome back. What will happen between the radius and the chord is one will bisect the other. So the radius will bisect the chord. These two are going to be bisected. And there's a really logical way of thinking about this. I'm going to quickly go over this in like 30 seconds. So if I draw these two segments in here, you're going to notice that AB is going to be the radius of circle B, as well as with BC. So we know that these two segments are going to be congruent. We also know that this segment here, BE, will be congruent to itself. So if you look at this, okay, and you're told that that BD is perpendicular to AC, the radius is perpendicular to the chord, so therefore I have two right triangles. These two triangles are going to be congruent because of hypotenuse leg. And because they're congruent, we can then therefore conclude that those two segments must be congruent. Okay, so therefore AE must be congruent to EC, or in other words, the radius will bisect the chord. The second theorem that I want to talk about is this guy right here. Okay, and if a line tangent to a circle, if a line, I should say, my grammar here is really bad. So if a line is tangent to a circle, then the line is blank to the radius. Now, there's a vocabulary word in here, and that vocabulary word is tangent. What does it mean for a line to be tangent to something? Well, when a line is tangent to something, or when two things are tangent to one another, okay, those two things are touching each other at one point and one point only. So, if you look at this, okay, I'm looking for a word, okay, that satisfies this statement. And again, the hint here is I'm looking for an angle, okay, between the radius and that tangent. The radius and the line, okay, between the radius and this line that's tangent to the circle. So, pause a moment and think about this. What's going to be the angle relationship between the radius and the tangent? Again, if you thought of the word perpendicular, then you are 100% correct. Okay? So the if a line is tangent to a circle, then the line will be perpendicular to the radius of the circle. Okay? And then the flip side is, okay, let's say now you're not told that the line is tangent, okay? But you know that the line is perpendicular. So you see how the logic there is like reversed, okay? If a line on a circle is perpendicular this time, okay, to the radius of the circle, so I'm looking at the second theorem here, or the second half of this theorem, okay? If a line on a circle is perpendicular to the radius, okay, which I just drew in there, then the conclusion is that the line is blank to the circle. What word am I looking for here? It's the reversal. It's the reverse idea of the of the top half of this theorem here. It's the reversal of this top half. So it's actually tangent. That's the word I'm looking for. Okay, so the line will be tangent to the circle. Okay. I'm reversing that concept, okay? I hope you guys can recognize that. So if a line is perpendicular to the radius, then therefore the line is going to be tangent to that circle. So here are the two concepts, okay, for this video as well as for the assignment that you are going to complete. That is the Google form that's posted in Google Classroom, okay? So here it is one more time. Again, I need you to take notes on this, so you should have this. All right, so I'm going to move on. All right, we're going to take a look at 4 examples together. So you're given this diagram where you have circle D, okay, and you're told certain segments about this circle. So you're told that DA, so segment DA is 5, segment BC is 8, segment AB is equal to 12, and you're asked to find out what if segment AB is tangent to circle D. So let's draw all over this, okay? So I know that AD is equal to 5, or DA is equal to 5, and then I know that BC is equal to 8, so that's just this little segment on the outside, and then I have AB is equal to 12. Pause for a moment, see if you can figure out how you can determine whether or not we're going to have a, whether or not AB is going to be tangent to this. And the hint I'm going to give you is, in order for AB to be tangent to circle D, we have to have a right angle in here. So something has to be related to this triangle, right? That's drawn. How are we going to show that AB is going to be tangent to that? Pause the video and think about this. So having thought about this, okay, or hopefully you press pause and you thought about it a little bit, okay? You hopefully some of you guys thought about filling in the other piece of the other segment here that's not directly stated, which is segment DC. DC happens to also measure 5 because DC is also a radius of the circle, right? So what I end up with is, okay, I end up with a triangle that looks something like this. So I have 5, I have 13, and I have 12. And I'm trying to show whether or not that AB is going to be perpendicular to AD. Well, in order for AB to be perpendicular to AD, what kind of triangle should this triangle be? It has to be a right triangle, right? So in order for us to show whether or not this is in fact a right triangle, these three numbers, 5, 12, 13, it must satisfy this very famous theorem, the Pythagorean theorem. It must satisfy the Pythagorean theorem, which says the leg squared plus the second leg squared must equal to the hypotenuse squared, which is 13 squared. And let's see if that is in fact the case. This is going to be 25 plus 144 is equal to 169. And as it turns out, it does equal. Both of these equal to 169. This is how we can show, okay, that AB is in fact perpendicular to AD. So yes, tangent. So again, this is the trick. In order to show whether or not two segments are perpendicular to one another, okay, or in this case, in order to show whether a line is tangent to the circle, you need to show whether or not it satisfies the Pythagorean theorem. Let's take a look at another example. And I encourage you to pause the video and think for yourself on to justify whether or not this is in fact perpendicular. So hopefully you press pause. And here we are again. I'm going to fill in all the different dimensions here. AB is equal to 4. And then I have AD is equal to 10. And CD is equal to 5. So really, I'm dealing with a triangle that looks something like this. Again, hopefully you've gone through the thought process and thought of this on your own. Okay, so now I'm dealing with 5 and 10. I was not told the full segment of that other leg there, okay? But I do know that BC should also equal to AB because BC happens to be the other radius, okay, of the circle. So therefore, the total segment there of the diameter is 8. So I need to see whether or not those three numbers there satisfy the Pythagorean theorem. If it does, CD is going to be perpendicular to is going to be tangent to circle B. So let's see. I have 8 squared plus 5 squared. Will it in fact equal to 10 squared? Let's see. So 8 squared, that's 64. 5 squared is 25. And 10 squared is 100. And as it turns out, no, they're not the same. So therefore, I say that CD is not tangent. So CD is not tangent to circle B. So this is the conclusion that we can draw as a result of this. Let's move on to the next one. And again, I encourage you to pause a video and try to think of this. Try to think about how to solve this on your own. So welcome back. If I take a look at this, I see that CD here, and now here you're told that CD is in fact tangent. So therefore, because it's tangent, the line tangent to the circle must form a right angle with the radius. So CD here, I don't know what that is. I'm asked to find out what it is. So BC, I'm sorry. So I'm dealing with a right triangle. I'm going to quickly draw that over here. Okay. So CD here, I don't know what that is. I'm going to call that X. All right. And then I have ED is 6. So therefore, the whole segment on the bottom here must be 12 then, because that's the diameter. That must be 12. And then I have the segment on the outside, AC, which is 15. I need to find out what this is. Well, isn't this just another Pythagorean theorem problem? As a matter of fact, it is. So therefore, I say x squared plus 12 squared is equal to 15 squared. And if I go through Pythagorean theorem, this is 144, and 15 squared is 225. I can then conclude that x squared is equal to 81, or x is equal to 9. Or in other words, CD is equal to 9. Let's look at the next one. And again, I encourage you to pause the video, okay, see if you can apply some of the concepts related to this video that I've talked about in the beginning. So one more time, this problem here, if you look at this, okay, it looks like a very similar setup where we have a radius, and I'm telling you EC and CF here are equal, right? So the chord, that means the chord is bisected. So that means we're going to need to utilize the information presented over here, okay? So we need to utilize these concepts, or in particular this one right here, okay? So again, in this problem, EC is equal to CF, okay? So pause the video now, okay, see if you can try this out, okay? EC is equal to CF. So if EC is equal to CF, I know that that must be true, okay? I also know that BC here is equal to 3. And I also recognize that I need to find out what EF and CD is equal to. Oh, there's also one other information. Radius of circle B is 5. So therefore, AB must equal to 5. Upon inspection, okay, I immediately, okay, notice something. What should the length of BD equal to? Right? BD should also equal to 5. So if BD is equal to 5, according to the segment addition postulate, BC and CD must also add up to 5, right? So therefore, I can say CD must equal to 5 minus 3. Or in other words, CD must equal to 2. So, but I still haven't figured out what EF is, right? Well, the thing is, if the chord is bisected, therefore the chord and the radius must be perpendicular. And if the chord and the radius is perpendicular, therefore I'm dealing with two right triangles. What do we know about segment BE? What do we know about segment BE? Segment BE is also the radius of the circle, is it not? Right? So segment BE is the radius of the circle, and that is also equal to 5. So if BE is equal to 5, I can then figure out what EC is. Because, again, I'm dealing with a right triangle. The right triangle I'm dealing with looks something like this. This is 3. This is 5. So, and I need to figure out what x is. If you immediately recognize this as a Pythagorean triple, then you're right. But if you don't, here it is, the execution of it. 3 squared plus x squared is equal to 5 squared. Then immediately I know that this is 9 plus x squared is equal to 25. Or x squared is equal to 16. Or finally, x is equal to 4. So if x is equal to 4 and x is this segment up here, EF, therefore, must equal to 8. Again, this video, okay, this the content that was talked about in this lesson, okay, in summary, we're talking about these two concepts here, which again heavily rely on the concept and skill of you being able to apply the Pythagorean theorem. And the one common theme here is the angles formed between the radius and the chord, as well as the radius and the tangent. They are all 90 degrees. Thank you for watching.